Washington, D.C., 1940. The city moved with a deceptive calm, as if unaware that half the world was already burning. Factories across America still built radios, refrigerators, and family cars. Laboratories ran on modest budgets. Politicians argued about neutrality. The United States believed the distance was enough to guarantee safety. But inside a narrow office on the top floor of the Carnegie Building, one engineer had already seen the storm approaching, and he was preparing a plan to confront it. His name was Vannevar Bush, an electrical engineer from Massachusetts, who had spent his life turning abstract ideas into machines that worked. He was the type of man most people overlooked. Quiet, methodical, more comfortable with slide rules and circuits than speeches or power. Yet he possessed something rarer than brilliance, the ability to understand how science could shift the balance of war long before the generals or politicians grasped what was coming. Bush had watched Europe collapse into chaos with growing alarm. Radar experiments in Britain were accelerating. German laboratories pushed the limits of physics under the pressure of totalitarian ambition. The pace of innovation overseas was terrifying, and the United States was not ready. Its research programs were scattered across universities, private companies, and military offices that barely communicated with each other. Bush realized that if America didn't centralize its scientific power, it would face the war with tools from the previous century. So he crafted a bold proposal, unlike anything the country had ever considered. A single organization uniting engineers, physicists, chemists, mathematicians, and industrial planners under one command. Not military, not political, but scientific. He believed that victory in the next war would depend not on the size of armies, but on the speed of innovation. Whoever mastered radar, explosives, ballistics, cryptography, optics, and computation first would control the battlefield. To most people in Washington, this idea sounded unrealistic. The government had never allowed civilians to direct military research, but Bush understood how to speak the language of power. He walked into the Oval Office and presented President Franklin D. Roosevelt with a simple, devastating truth. Unless the United States reorganized its research, it would lose a war before it even entered it. Roosevelt, with his instinct for strategy, recognized the urgency. Within minutes, Bush secured approval for what would become the Office of Scientific Research and Development, an institution that would soon coordinate more than 6,000 scientists across the nation. This moment marked the beginning of a silent revolution. While newspapers followed troop movements and political debates, Bush built a new kind of battlefield. One made of equations, prototypes, test ranges, and laboratories running day and night. Under his leadership, engineers refined radar to detect aircraft hours before they reached their targets. Chemists created explosives more powerful and reliable than anything used in the First World War. Mathematicians developed trajectory tables that transformed artillery accuracy. Physicists worked on proximity fuses that would soon destroy enemy aircraft without direct hits. Entire industries, once focused on consumer goods, were converted into engines of war with breathtaking efficiency. Bush wasn't designing weapons himself. He was designing the system that made weapons possible, and that system changed everything. For the first time in American history, science moved faster than the battlefield. Research wasn't a reaction to enemy threats. It was a force that anticipated them. This shift would redefine the war and reshape the world that followed it. But Bush's influence extended far beyond laboratories. He knew innovation meant nothing without organization. So he tore down barriers between universities and the military, forcing institutions that usually competed with one another to collaborate under a national mission. He negotiated with industrial leaders, merged public and private research, and ensured new technologies reached soldiers before enemy tactics rendered them obsolete. America's scientific machine began turning with unprecedented speed, because one engineer understood that victory required more than courage. It required ideas. In the background of every major breakthrough of the early war years, Bush was there, orchestrating, coordinating, pushing. His presence was quiet, but constant, the kind of influence that disappears into the achievements of others. He didn't seek credit, fame, or command. He wanted results. And the results were about to change the trajectory of World War II. As America prepared to enter the conflict, Bush stood at the center of a growing network of laboratories and test facilities that stretched from MIT to California. Radar arrays rose along coastlines. Factories expanded. Universities transformed into military research hubs. Innovation replaced complacency. Science replaced speculation. For the first time, the United States was not just catching up, it was accelerating. And as we uncover this hidden chapter of history, remember this. If you want more forgotten stories of engineers who quietly shaped the fate of nations, consider subscribing so you don't miss what comes next. Because what happened after 1940 would push Bush into decisions far more complex than equations and circuits. Decisions that questioned not only the future of the war, but the future of humanity itself. Was Bush preparing to save the world, or to unleash something far more dangerous? When the United States officially entered the war in December 1941, most Americans imagined a conflict fought with battleships, rifles, and aircraft. But inside the corridors of the newly expanded Office of Scientific Research and Development, Vannevar Bush saw a very different picture. He understood that the war's outcome would hinge on something far less visible: the speed at which ideas could be transformed into functioning machines. For Bush, the battlefield was not defined by front lines. It was defined by laboratories. His first priority was radar. Before the war, radar existed only as a fragile experiment, scattered across a handful of academic institutions with limited coordination. Britain had demonstrated its potential during the Battle of Britain, but the United States lacked a system capable of detecting enemy aircraft or submarines across vast oceanic distances. Bush saw radar not as a defensive tool, but as a way to reshape the nature of air and naval combat. He created the Radiation Laboratory at MIT, an institution that would become one of the most productive scientific centers in history. Inside the Rad Lab, physicists and engineers worked in brutal schedules, testing components that pushed the boundaries of electronics. They transformed crude early radar into precise microwave systems, capable of guiding pilots through fog, tracking submarines beneath the waves, and locating enemy aircraft long before they could strike. These advancements didn't merely support combat operations. They prevented disasters, saved convoys, and helped the Allies reclaim control of the Atlantic. But radar was only one part of a much larger ecosystem. Bush believed that innovation had to be synchronized across domains: air, sea, land, and industry. To achieve this, he reorganized how researchers communicated with manufacturers. Experiments were no longer isolated projects. They became components of a coordinated national engine. Factories received blueprints in days, not months. Testing fields relayed data in real time. Every successful prototype immediately triggered the next phase of production. Bush had effectively created a supply chain for ideas. One of the most transformative breakthroughs to emerge from this system was the proximity fuse. Traditional anti-aircraft shells required a direct hit, an almost impossible task against fast-moving aircraft. Engineers under Bush's direction developed a miniature radar device small enough to fit inside a shell, detonating it automatically when it approached a target. This invention revolutionized air defense overnight. In the Pacific, it tore through kamikaze attacks. In Europe, it shredded German V-1 rockets. Pilots reported watching enemy aircraft disintegrate in mid-air without understanding how. Few knew that the mechanism behind this new power had been refined under Bush's supervision. Bush also pushed advancements in medicine, an area often overshadowed by machines, but crucial to survival. He funded research that led to the mass production of penicillin. ensuring wounded soldiers received life-saving treatment. He oversaw improvements in blood plasma storage, battlefield surgery tools, and treatments for tropical diseases. These medical innovations saved thousands of lives, and they emerged from the same engine that produced radars and fuses. Meanwhile, mathematicians under Bush's network developed advanced ballistic tables and computational machines. These devices, PTK, precursors to the modern computer, processed equations faster than any human team. Artillery crews gained unprecedented accuracy, turning bombardments from guesswork into strategic precision. Naval gunners could track moving targets with algorithms that predicted their paths. Even bombing missions became more efficient, guided by data instead of instinct. Bush's strength was not in building any single device. It was recognizing how each innovation supported another, forming a technological ecosystem. He made engineers from unrelated fields collaborate, often forcing people who had never met to work side by side. He rejected bureaucracy, cut through military hesitation, and ensured ideas reached the battlefield while they still mattered. Under his leadership, time became the most valuable resource, and he made sure the United States used every second. But innovation brought new challenges. As laboratories expanded and scientists gained influence, Bush had to fight political pressure. Some military leaders resisted civilian oversight. Others feared the pace of research was out of control. Bush found himself navigating the tension between military authority and scientific independence. He knew that interference could slow progress, yet complete autonomy carried its own risks. Balancing these forces required a level of diplomacy most engineers never face, yet Bush handled it with the same precision he applied to circuits and diagrams. As 1942 turned into 1943, the OSRD had become a sprawling network of thousands of engineers and scientists, from the largest universities to the smallest workshops. Bush didn't control them with force, he motivated them with purpose. He reminded them that every breakthrough, no matter how small, had the potential to change a battle, save a convoy, or protect a pilot. He understood that the war was not a single conflict, but a mosaic of countless technical challenges. Solving each puzzle brought the Allies closer to victory. Behind the curtain of wartime production, Bush's influence reached into factories, briefing rooms, air bases, and naval yards. His fingerprints were on radars, carried by bombers, fuses packed into artillery shells, torpedoes fired from submarines, and medical kits strapped to medic belts. Yet he remained invisible to the public. Soldiers never heard his name. Newspapers rarely mentioned him. His victories belonged to the nation, not to his ego. But beneath all this progress, another project was emerging. One so secret, so unprecedented, that even Bush hesitated to involve himself fully. It was a discovery with consequences no engineer had ever faced, and it would force him to question the very foundation of scientific responsibility. Was Bush guiding the future of warfare, or losing control of the forces he helped unleash? By 1943, Vannevar Bush had transformed American science into an engine operating at full speed. Radar networks stretched across coastlines. Proximity fuses changed the rhythm of anti-air warfare. New medicines reduced battlefield deaths, and computational machines improved accuracy everywhere from artillery batteries to naval gunnery. But as the war intensified, a new question began to rise inside the OSRD. One that didn't involve better detection, faster calculations, or more efficient weapons. It involved energy, but on a scale no one had ever controlled. Reports from Europe hinted that German physicists were investigating nuclear fission. The discovery shocked many, but Bush wasn't surprised. He had predicted that once the world entered a conflict driven by scientific talent, nations would race not only to build machines, but to pursue entirely new laws of physics. And if the Germans were indeed exploring atomic energy, the United States couldn't afford to ignore it. Bush understood instantly that this was different from radar or medical research. Nuclear fission wasn't just another project. It was a frontier that could reshape the meaning of warfare. He also saw something else. If left uncoordinated, dozens of American laboratories would compete, duplicate experiments, waste valuable time, and risk falling behind a ruthless enemy. He needed to centralize this effort before it spiraled into chaos, so he made a decisive move. He went directly to President Roosevelt and warned him that atomic research could not follow the usual pathways of science. It required secrecy, coordination, and resources no single institution could manage alone. His proposal was radical: create a new program, hidden from the public and controlled with absolute discipline. Roosevelt agreed, and within weeks the Manhattan Project began taking shape. Although Bush was not the scientific leader of the Manhattan Project, that role belonged to physicists like J. Robert Oppenheimer and General Leslie Groves. He defined its structure. He set its boundaries, selected its leadership, controlled its funding, and ensured no outside force interfered with its progress. His influence was quiet, but decisive. The project existed because he built the administrative skeleton that allowed it to grow without breaking under its own weight. Bush's relationship with the Manhattan Project was complex. On one hand, he recognized the catastrophic potential of nuclear weapons. On the other, he knew the consequences of allowing the Axis powers to develop them first. He wasn't driven by ambition or fear, but by a cold calculation. If the United States hesitated, the world could fall under the control of a regime capable of using such a weapon without restraint. Yet, as the project expanded, from university basements to massive secret cities like Oak Ridge and Hanford, Bush worried about something deeper than military advantage. He feared that once the bomb existed, it would alter global politics forever. Science had always been a tool for progress. Now it threatened to become a permanent instrument of destruction. The line between innovation and devastation was becoming dangerously thin. Inside the OSRD, other technological revolutions marched forward. Engineers developed new sonar systems for submarine warfare, infrared detectors that allowed soldiers to see in darkness, and communication devices that shrank the distance between commanders and troops. But none of these accomplishments eased Bush's concerns. He sensed that the Manhattan Project was consuming scientific resources at an unprecedented rate. Brilliant physicists who once worked on radar were now behind barbed wire, calculating critical masses and neutron flux. Laboratories that once developed instruments for aircraft now built components for weapons that could destroy entire cities. Bush tried to maintain balance. He ensured radar research continued, pushed for improvements in electronics, and kept medical projects funded. But the gravitational pull of the atomic program grew stronger every month. Despite his attempts to keep the scientific machine stable, the war's most secret project increasingly dominated American research. Publicly, Bush remained invisible. Few Americans could imagine that a quiet engineer, hidden behind government doors, was coordinating the largest scientific effort in human history. Soldiers who depended on radar to land safely at night never knew whose ideas brought the technology into existence. Pilots who watched proximity fuses detonate. Enemy aircraft had no idea that the device they trusted originated from Bush's organizational command. Even within the military, many officers saw only the results, not the architect behind them. As the atomic program approached its climax, Bush pushed for something he believed was essential: post-war scientific responsibility. He feared that once the bomb existed, nations would race to build even deadlier variations. He argued that scientists needed a voice in political decisions involving weapons of unprecedented power. Bush wasn't naive. He understood human nature, but he hoped that reason could restrain the destructive momentum of technological progress. Meanwhile, the Manhattan Project moved closer to its goal. Laboratories in Los Alamos ran uninterrupted experiments. Engineers refined implosion mechanisms. Chemists separated plutonium with increasingly efficient methods. Test sites emerged in the deserts of New Mexico. Every success pushed the United States closer to the moment when science would step into territory no nation had ever entered. The tension between innovation and morality grew sharper. Bush believed in the power of knowledge, but he also understood that knowledge without limits could reshape civilization in irreversible ways. The burden weighed on him, even as his leadership remained essential to navigating the most complex scientific era the United States had ever experienced. Behind the scenes, he continued to guide the broader war effort. Breakthroughs in navigation instruments improved bombing accuracy. New electronic devices increased pilot survival rates. Improved torpedo mechanisms reduced naval losses. The scientific machine Bush built was operating with near mechanical precision, feeding the war with constant innovation. Yet one question haunted him. Once this war ended, what kind of world would remain? Science had given nations the tools to defend themselves, but soon it would give them the tools to destroy themselves. And Bush, more than anyone, understood that the line between these possibilities was becoming dangerously thin. As the Manhattan Project neared its final stage, Bush found himself confronting a reality even he hadn't fully anticipated. The next breakthrough wouldn't just decide a battle, it would decide the future of humanity. Had Bush unleashed a force he could no longer control, or was he the only one who truly understood the consequences of victory? By early 1945, the war in Europe was collapsing. Radar-guided bombers roared over German cities. Proximity fuses shattered Luftwaffe counterattacks, and Allied fleets crossed oceans with confidence built on the technology Bush had organised. Yet, even as victory approached, Bush felt none of the relief the public expected. Instead, he faced the most difficult moment of his career, a decision that had nothing to do with equations or efficiency, but with morality. The Manhattan Project had moved faster than anyone predicted. Scientists who once doubted the feasibility of atomic energy now held in their hands detailed calculations proving the destructive power of the devices they were building. Test assemblies were nearing completion. Installations in the desert stretched across the horizon. Bush had been present at every major administrative milestone, but the deeper he went into the project, the more he understood the dilemma it posed. He had argued for the bomb's development because the alternative, a German atomic weapon, was unthinkable. But Germany was now on the brink of defeat, and the centre of global danger had shifted to the Pacific. Japan was still fighting with ferocity, and projections for an invasion of the Japanese mainland predicted casualties in the hundreds of thousands. The bomb, once a theoretical safeguard against Hitler, was becoming a very real instrument for ending the war. Bush watched reports come in from the Pacific, kamikaze waves crashing into American carriers, island battles that drained entire divisions, air raids that still couldn't break Japan's resistance. Military leaders demanded a decisive blow. The bomb offered that. Yet Bush hesitated. He feared that using such a weapon would open a door that could never be closed. Inside Washington, the discussions grew intense. Generals saw strategy. Politicians saw leverage. Scientists saw responsibility. Bush saw all three at once. He knew that no matter how the war ended, the world would eventually learn what America had created. And once the existence of nuclear weapons became public, other nations would race to build their own. The United States wouldn't remain alone in this new frontier. The balance of power would shift forever. Still, the bomb wasn't just a symbol. It was a machine built for war, and wars end with decisions, not theories. Bush understood that engineers didn't get to choose the world their inventions entered. They could only choose whether to act or remain silent. With the lives of millions hanging in the balance, silence wasn't an option. In July 1945, the first atomic test, codenamed Trinity, lit up the desert of New Mexico. Bush wasn't at the site, but the message that reached his desk confirmed what he already suspected. The weapon worked. The age of nuclear power had begun, not with a scientific revelation, but with a fireball that erased the boundary between innovation and annihilation. As the war moved toward its final chapter, Bush prepared reports for President Truman outlining the consequences of the atomic age. He stressed the need for international cooperation, scientific oversight, and transparency. Safeguards he knew would be difficult to enforce once nations understood the strategic value of nuclear weapons. He argued not only for victory, but for restraint, yet even he recognized that restraint was often the first casualty of war. When the bombs fell on Hiroshima and Nagasaki, Bush received the news with a complex mixture of relief and dread. Relief that the war would soon end. Dread because he knew what would follow. The public saw power, military leaders saw dominance. Bush saw something else entirely. A permanent shift in human possibility, a point of no return. In the months that followed, he fought fiercely to ensure that the future of atomic research would not be swallowed by secrecy or militarization. He wrote long memoranda warning that science could no longer operate without ethical boundaries. But he also understood that the United States had entered an era where those boundaries would be tested every year, in every conflict, by every nation seeking advantage. Bush had spent his life believing that knowledge, when organized correctly, could protect humanity. Yet now he stood at the edge of a new reality. Innovation had given humanity the power to destroy itself, and he knew that this power would only grow. As the war ended, Bush faced a question far more personal than any scientific challenge. Had he helped save the world? Or had he set the stage for a future even more dangerous than the war he had just helped win? When the war ended in August 1945, celebrations erupted across the world. Streets filled with parades, flags, noise, and relief. Factories that had once produced instruments of conflict returned to civilian goods. Soldiers began the long journey home. But for Vannevar Bush, victory did not feel like closure. It felt like the beginning of another, far more complicated battle, one that could not be fought with planes, ships, or laboratories. Bush understood instantly that the true impact of World War II would not be measured by ruined cities or rewritten borders. It would be measured by the scientific forces unleashed during the conflict. Radar had changed how nations perceived distance. Electronics had lifted machinery into a new era of precision. Medicine had transformed battlefield survival, and the atomic bomb had redefined the limits of destruction. Every part of this new world contained traces of the system Bush built. But not all traces were equal. Some represented progress, others represented danger. In the final months of 1945, Bush began a new mission, shaping the future of American science in peacetime. He knew that research could not simply return to pre-war academic habits. The war had shown that coordinated scientific effort was not only possible, it was powerful. And if left unmanaged, that power could accelerate without purpose, without ethics, without national oversight. So Bush wrote a report that would influence the next century. Titled Science, the Endless Frontier, it argued that the United States needed a permanent foundation for scientific research. Not a wartime machine, not a military branch, but a national strategy. He proposed federal funding for universities, grants for young researchers, and long-term investment in fields that had barely existed before the war. It was a vision meant to ensure that innovation remained a tool for human development, not only military advantage. This report led directly to the creation of the National Science Foundation, an institution that would shape American education, technology, and research for generations. Bush believed that knowledge should not be controlled by governments or corporations alone. It should be accessible, encouraged, and protected. In a way, it was his attempt to counterbalance the consequences of the Manhattan Project, a way to guide the power of science back toward growth instead of destruction. But even as he built this new scientific landscape, Bush remained haunted by the atomic age. He spent years warning presidents, senators, and military leaders that nuclear weapons required strict international agreements. Without cooperation, he feared an arms race that would destabilize the entire world. His fears were soon justified. The Soviet Union developed its own bomb. Other nations followed. The Cold War began, shaped not by ideology alone, but by technology that had been born in the laboratories Bush helped organize. He had created a new engine. But once the war ended, the engine continued running without him. And yet, despite the shadows left by nuclear power, Bush's legacy cannot be defined by the bomb alone. He had revolutionized how nations integrate science into strategy. He had established research infrastructures that shaped medicine, engineering, computing, and countless other fields. He had proven that scientific organization could determine the outcome of global conflict. And he had shown that innovation without coordination was not innovation. It was chaos. Still, his influence remained largely invisible. Soldiers remembered the victories, pilots remembered the missions, citizens remembered the celebrations, but few remembered the engineer who orchestrated the behind-the-scenes transformation. Bush never sought fame, and he never asked for recognition. His impact existed in the machines others used, the systems others managed, and the breakthroughs others credited to themselves. History often celebrates heroes who stand on battlefields. Bush fought a different kind of war, one conducted through ideas, blueprints, and decisions made in quiet offices far from the front lines. In the decades that followed, Bush watched the world embrace the technologies he helped bring to life. Commercial aviation grew from wartime electronics. Modern computing evolved from early wartime calculators. Communication networks expanded from military research. Medicine advanced through innovations first tested under crisis. Every new generation, whether aware or not, lived in a world shaped by decisions he made when the outcome of the war was uncertain. Yet the question remained, had he guided humanity towards safety, or had he accelerated the arrival of new dangers? Even Bush couldn't fully answer that. Science is not moral or immoral by nature. It becomes what humanity chooses to make of it. And Bush's genius lay in recognizing that scientific progress, once unleashed, cannot be slowed, only directed. His legacy is a paradox. He built the system that empowered American strength, but also the system that demanded constant vigilance. He armed a nation, but also warned it. He expanded the boundaries of knowledge, but feared where new boundaries might lead. Few men have influenced so much while remaining so invisible. And maybe that's why his story matters. Not because he invented a single weapon or designed a single machine, but because he built the environment in which all of them became possible. He showed the world that engineers don't only shape technology, they shape the future. As we look back on the man who transformed science into strategy, industry into innovation, and laboratories into engines of war, one question remains. Did Vannevar Bush secure a safer world? Or did he unknowingly ignite a race humanity may never fully control?